My name is David Romps, and I'm going to be speaking about the convective dynamics of nuclear winter. My not-so-hidden objective with this talk is to get at least one person in the audience interested enough in this topic to begin doing research on it. It's a very important topic, and also I think it's very rich with important and fundamental atmospheric science questions. So first of all, what is nuclear winter? Well, it's the phenomenon that occurs potentially after a nuclear war. Nuclear warheads would set ablaze entire metropolitan areas at once, and once ablaze, that large area on fire could generate a firestorm plume that through convective dynamics could loft soot up into the vicinity of the tropopause. And once there, radiative lofting can act fairly quickly to get that soot firmly placed into the stratosphere, where it can have a lifetime not of weeks like in the troposphere, but on a timescale of years. And sitting around in the stratosphere for years, it is blocking the sun the entire time, dimming the earth, and leading to crop failure. Now this is a potentially catastrophic kind of event. As shown by Xie et al. In 2022, they tabulated this table of consequences for different types of nuclear war. And there's a lot of numbers on here, so I'll just focus in on the best case scenarios that they came up with. If we consider a nuclear conflict between India and Pakistan, there are 52 million people who would be killed directly from the nuclear conflict, but almost 1 billion people would die from starvation due to the climate impact of that regional nuclear war. And if the United States and Russia were to be engaged in a nuclear war that also involved China and Europe, then we'd have 360 million people dead from the direct conflict, but over 5 billion people, best case scenario, killed from starvation. That's the vast majority of the human species. So this is potentially catastrophic indeed. And you might say, well, nuclear war is just not that likely, so I shouldn't worry about it, even if the outcome would be catastrophic. But I argue it's not. It's actually likely. And in fact, there have been several occasions where we've come very close to nuclear war. These two individuals, Vasily Arkhipov and Stanislav Petrov, single-handedly prevented nuclear war. Vasily Arkhipov in 1962 was the lone dissenting vote against launching a nuclear warhead. And Stanislav Petrov disobeyed the orders he was supposed to follow and did not trigger the launch of a full-scale nuclear attack against the United States. In other words, we can name two people who single-handedly prevented nuclear war, and these are two people to whom you and I owe our lives. Not to date myself, but I would not have been born if it were not for Vasily Arkhipov, and I would have been vaporized if not for Stanislav Petrov. So it's a very important topic, and yet if you look crudely at the amount of research that's being done on nuclear winter, it pales in comparison to the amount of work that's being done on global warming. This is a very crude metric, of course, that I've done here to type these terms into Google Scholar, but searching for global warming gives you over 3 million hits, whereas nuclear winter is orders of magnitude less at only 17,000. So much more research is needed on this topic. Now, I also argue that not only is nuclear winter an important thing to be researched, but it can also be beneficial to the atmospheric scientist, because nuclear winter is so full of fundamental science questions. From the kind of convective dynamics that would be responsible for lofting soot into the upper troposphere or in potentially lower stratosphere, to microphysics that would dictate how much of the soot is actually retained in the updraft all the way up into that emplacement around the tropopause, how much of it instead rains out. Then there's radiative lofting that combines radiative transfer and convective dynamics and large-scale motions and shear. And finally, there's microphysics and photochemistry that then dictate how that soot ages in the stratosphere, which alters its optical properties and its sedimentation rates. So all very important areas with big uncertainties at present in terms of how they affect the potential for nuclear winter. Now, I'll give you here a case study, just an example of how it is my group has interacted with nuclear winter. We've found that actually there's a bit of a virtuous interaction here. We're able to use our understanding of atmospheric convection to provide some insight into the risk of nuclear winter. But then also, surprisingly, thinking about nuclear winter has allowed us to identify opportunities for better understanding basics of atmospheric science, and atmospheric convection in particular in our case. And so I'll just walk you through that. First, I'm going to explain to you how it is we've used our understanding of atmospheric convection to improve our assessment of the risk. So this story begins in 2018, where Los Alamos National Lab published a study that said that nuclear winter is highly unlikely. So they ran a simulation, pictured here, of a large urban area on fire and tracked what happened to the soot in the convective plume. And that plume only got up to about 6 kilometers, which is far below the tropopause, which then allows that soot to be rained out on the time scale of weeks, rather than retaining itself in the stratosphere for years. And so based on this simulation, the authors concluded that the probability of significant global cooling, in other words, the probability of nuclear winter, is highly unlikely. Now, a curious feature of that study is that they omitted water vapor from their modeling. So there's no water vapor in that plume. And so it begs the question of whether or not that's okay. Now, if we think about how much heat is released in a fire, depending on where you are in the flame, you could be 500 Kelvin warmer than the ambient air. You could be 1,000 Kelvin warmer than the ambient air. So it's just really an enormous temperature anomaly that you have from the flames of combustion. On the other hand, the water vapor that's just lying around in the ambient air provides an equivalent sensible heating, if released, around the order of 25 Kelvin. That's what it would be if it were about 1% water vapor by mass. And so obviously 500 K is much bigger than 25 K, and so this is kind of the intuitive justification for saying that water vapor just shouldn't matter for these firestorm plumes, and so we can ignore it. But actually, it's not okay, and the reason it's not okay to ignore water vapor is that that large temperature anomaly is quickly depleted through entrainment and also through the action of adiabatic expansion. This is the result of this figure here is a result of a direct numerical simulation performed by Nathaniel Tarshish, where the solid black curve shows you that temperature of that firestorm plume quickly decreasing as you get up off the surface, and then further decreasing through entrainment and expansion until it hits the dashed black curve, which is the environmental temperature profile in this case. And so this is a case where we see we're simulating an entire urban area on fire, or something equivalent, and we see that the firestorm plume reaches this level of neutral buoyancy at about 2 kilometers. Now it'll overshoot that height, and so go a little bit higher, but it'll end up putting its soot in the lower troposphere. On the other hand, if we had water vapor, what happens? Well, this is the simulation without any water vapor. This on the left here, trying to emulate what was done in the Los Alamos study as closely as possible. And indeed, we see the soot only going up to 6 kilometers. But if we add back in the water vapor, that soot goes straight to the tropopause. And so we can say that actually nuclear winter is still very much a real possibility. So that was an example of using our understanding of atmospheric convection to improve our assessment of the risk of nuclear winter. But what about in the other direction? How about nuclear winter giving us some guidance on what types of atmospheric science questions to go after? Well, I can give you an example of that. In 2021, we deployed stereo cameras to the Houston area as part of the Tracer campaign to look at the interaction between aerosols and convection. It involves putting 2 cameras out there, and we can stereo reconstruct what's in the field of view, including getting the distances and heights and speeds and widths, etc. of clouds. And as we were looking at the data from those cameras, we discovered that in the mornings, sometimes we'd have these convective clouds, these cumulus clouds, that seemed to be pinned to particular locations. They would have mass flux flowing through them, but they weren't advancing along east, west, north, or south. They were staying over their locations. Now, pretty obviously a consequence of maybe some topography or some industrial heat source. And so you'll look at that and say, well, is this just a nuisance? And I think if I hadn't been thinking about nuclear winter, that's exactly what I would have thought about these clouds. But having nuclear winter in the back of my mind made me realize, and made us all realize actually that we're working on this, that this is an opportunity. That this is an example of a steady, moist plume driven by, potentially, a surface buoyancy source. So we used the stereo cameras to identify where these plumes were originating and discover that indeed they are sourced by industrial heat sources. And not only that, but we can use the Texas Commission on Environmental Quality data to identify exactly what the buoyancy flux is in this location. So now we have a data set on the environmental conditions and on the moist convective plumes themselves in a statistical steady state and the buoyancy sources from the ground. So we have a very nice analog for problems that are really relevant for nuclear winter. And so then we can begin to ask ourselves, well, can we actually predict mornings when we see just these pinned clouds? Can we identify or predict when we'd get clear sky conditions, or pinned clouds only, or widespread convection? And if we are not yet ready to do that successfully, then are we really prepared to predict the risk of nuclear winter? So that's the kind of question that these kind of data pose, and we're beginning to go after some of those questions. I want to note that the first authors of these papers were not myself, but they were Nathaniel Tarshish on the left, who was a graduate student at Berkeley and is now a postdoctoral fellow at Harvard, and Rushan Oktem on the right, who is a project scientist at Berkeley. So in summary, I just want to say again that nuclear winter is an important problem. This has potentially catastrophic implications for not just the people in the countries going to war, but all of us, and even the fate of humanity itself. And that is reason enough for us as a scientific community to be giving this topic more attention than we already do. But for the individual scientist, there are the additional co-benefits of the fact that nuclear winter is so closely connected to fundamental questions in atmospheric science. And so I'm hopeful that from this talk, there's one person in the audience who's not formally worked on nuclear winter who might consider applying their skills to it. Thank you so much for listening.